Yeah, okay.
Okay. Okay. Thank you, Professor Yi. And good afternoon, everyone, and good morning, Professor Ping Ho. And my report is the development of failure theories of composite material. My report has also have 4 parts. So we all know that the composite is very special compared with metal materials. It is a mixing of many kinds of material together according to a certain rule, which has many good characteristics, including designable material properties, high specific strength and stiffness, good fatigue and corrosion resistance. It can meet the performance requirement of aircraft structure more perfectly. So it has widely used in aircraft structure in the past 50 years. Currently, the use of composite material in civil aircraft structure has reached 50% in weight, and its relevant standard specification and design and manufacturing documents have been formed by government, industry, and major aircraft manufacturing company. Behind these achievements are the result of our fundamental theory research on composites, including failure criteria. These basic theory have laid a solid foundation for the application of composites in aircraft structure today. In the following, I will reveal the development of composite failure criteria and the process of our understanding of these failure criteria. So let's first introduce the phenomenological theory of failure criteria. These are the simplest and the early emergence of the strength criteria for composites. The maximum stress criterion and the maximum strain criterion. The idea is the same as the strength criterion for metals. Damage occurred when the maximum stress or maximum strain reach a specific value, which are the strain of the material in corresponding direction. The criteria only considered the relationship between the unidirectional stress and strain and the material failure, and ignore the interaction between the multidirectional stress and various failure modes. To solve this problem, people further developed the strength criteria. Side-Hill criterion is a direct adaptation of the classical missile yield criteria so that it can be applicable to the isotropic material with different behavior in tension and compression. Furthermore, Tsai and Wu proposed a more general form of Tsai-Hill criteria. They believe that the existing phenomenological theory failure criteria are attributed to various special cases of high-order tension polynomial failure criterion, with second-order polynomial as the main computational criteria. In general, the more efficient and that need to be experimentally determined in such strength criteria, and the more accurate the prediction. Actually, phenomenological failure criteria are empirical criteria, which are to some extent the fitting of the experimental data. And their accuracy is based on a large number of experimental data and do not reflect the complexity, the complex damage mechanism of composite material. Relatively speaking, the accuracy of these criteria is not enough, but cost is high. With the deep understanding of the mechanical property of material, of composite material and the accumulation of large number of engineering applications, people cannot satisfied with the level of phenomenological strength theory. The so-called phenomenon refer to the damage criteria obtained by the generalized test date without considering the damage mechanism of composite material. In 1996, the report, New Material for Next Generation Commercial Transport, put forward by the 5 professional committees in the United States, emphasized that the difficulty of the predicting the mechanical behavior of composite material. The main problems are the determination of complex stress state of composite structure, damage mechanism related to load history, residual stress induced by manufacturing, and the damage mechanism and the corresponding failure criteria. The concept of the strength criteria based on the damage mechanism is clearly proposed here. The report had an important impact on our research work at that time. The main work of the accelerated insertion of material program carried out in the United States in 2001 includes established failure criteria based on the physical model and multi-scale analysis model, and reliable predict initiation and propagation of damage by material properties, considering material microscale property and process effects. I think this idea was very enlightening at that time, and the complexity of the failure mode and the importance of failure process of composite material have been recognized. It did guide the development direction of the research of composite material criteria later. In 2005, NASA revised the aviation research and development plan, clearly proposed the concept second generation prediction. And the key point are the physically based failure criteria. At that time, some composite researchers were very optimistic. They believe that the research and establishment of the second generation strength criteria could be completed within 10 years. That is from 2000 to 2010. I remember that this was the will put forward by a Japanese scholar. In fact, we are too optimistic. Up till now, our research on prediction of composite strength is still in progress. The design of the aircraft structure mainly depends on the traditional building block test, which cost a lot, and cost a lot of money, time and money. The development of physical-based failure criteria. The failure of composites has a very variety of failure mode. According to the dominating constituent of failure, it can be divided into fiber failure and matrix failure. Different failure modes have a different failure mechanism. For example, under the longitude compression load, the main failure mechanism is a fiber kink bond caused by initial misalignment defect. In order to better characterize the failure behavior of composites, the physically based failure criteria are established according to a different failure mode, in which each failure mode is described by a special equation. Hansen and Rotem proposed the first physically based criteria for different failure modes. 4 failure modes are considered: fiber tension and fiber compression, matrix tension, and matrix compression. However, the physically based criteria does not always mean that the criterion for all failure mode is physically based. And in the Hansen failure criteria, fiber tension failure is described by the polynomial criteria, while the fiber compression failure is described by the maximum stress criterion. And the matrix failure criterion is established by the theoretical analysis based on the failure characteristics and the strength of the composite material under typical stress state. And Professor Chen of Nanjing University of Aeronautics and Astronautics modified the Hansen failure criteria by theoretical analysis. In addition, the concept of stress correcting factor is proposed considering the effect of the fiber progress failure on matrix failure. The effect of sigma 11 on matrix failure is introduced by the correcting the stress component by the factor. And by comparing the modified failure criterion with the original failure criterion and the experimental data, it is shown that the modified failure criterion has a better prediction accuracy. And the Hansen failure criteria has a simple form and take into account the key process and the different failure modes. So it plays an important role in the finite element simulation. The Hansen failure criteria is integrated in the Abacus commercial software for simulation, the failure behavior of composites. However, as the research progresses, it is found that the prediction accuracy of Hansen failure criterion was poor in some stress state. And for example, large amount of experimental data show that the fiber tension failure was basically independent of longitude shear stress. For transverse compression failure, the failure strength prediction for local stress state is on the conservative side. Within the deep study of the failure mechanism, Park developed a strength criteria based on the moral column law. It is believed that the transverse failure of the composite material may occur in any plane parallel to the fiber, when and where it fail is related to the stress state of the corresponding plane. Park failure criteria is divided into two parts: fiber failure and interfiber failure. The maximum strain criterion considering Poisson effect is adopted for the fiber failure. The interfiber failure is determined according to the stress state acted on different planes. In the application of interfiber failure criteria, it is necessary to calculate the stress state on different planes according to the stress transform form, and then bring them into the failure criteria for calculation. When the stress state on the plane meets the failure criterion, and the composite will fail on this plane. Park failure criteria has made a great improvement in interfiber failure. In addition, it can also give the orientation of the matrix crack, which is great significant for the prediction of matrix failure in composite. However, failure judgment is required for each angle plane, which is complex in the programming and inefficient in calculation. Inspired by the Park failure criteria, NASA's Langley Research Center, together with other research institutes, proposed Luck theory criteria. Luck theory criteria are proposed based on the research of failure mechanism of composites and longitude compression. It is considered that the key failure mechanism is the kink bond failure and the longitude compression during the initial misalignment. As the research progressing, 4 Luck failure criteria was developed, and more factors that have impact on the strength are taken into account. 3 kinds of failure mode are considered in Luck 5 failure criteria: fiber tension and failure, fiber compressive failure, and matrix failure. According to the location and the thickness of the failure layer, the analysis model is established and the calculation formula of the in situ strength is obtained. Log5 failure criteria give more accurate strength prediction of composite and longitude compression load. Similar to Park failure criteria, Log5 failure criteria can predict the crack angle of the matrix failure. However, failure judgment is required for each angle plane, which is complex in the programming and inefficient in calculation. Log5 is a great criteria, and we have successfully predict the open hole compression strength using Log5 criterion in our research program. Here, I pay tribute to Professor Ping Hong. In order to solve the problem of low efficiency in solving the angle fracture surface with Log5 criteria based on the idea of efficient search algorithm proposed by previous scholar for Park criteria and the characteristics of the failure index curve of the Log5 criterion, we developed efficient solution algorithm for Log5 failure criterion. The computation time is only 20% of the original Log failure criterion, which significantly improved the computation efficiency. The multi-scale analysis method is another way to predicting failure of a composite material based on the physical model. The composite material can be considered as a structure which can be divided into multiple scales, such as micro scale, meso scale, and macro scale. Strictly speaking, the material failure should start from the micro scale and then extended to meso scale, and finally to the macro scale. And therefore, through the multi-scale method, we can determine the diameter process of composite material and their loading bear capability and precision. The score of the multi-scale analysis method is to establish accuracy and efficient stress-strain relationship between the micro scale and macro scale. Multi-scale analysis method can be roughly divided into two categories. One is to establish the calculation formula of multi-scale stress through the theoretical analysis, and the other is establish the stress amplification matrix based on the calculation of the RVE, that is the representative value element, to realize the conversion of the micro and macro. In terms of the theory-based failure criteria, we proposed failure criteria which contain two parts, transverse failure and longitude compression failure. For the transverse failure, the core idea is to establish the relationship between the microstress near interface and the microstress, and then to substitute the microscale stress into the substitute failure criteria to predict the strength under the complex stress. And here the calculation formula of the multi-scale stress is established. And compared with the existing experimental results, the proposed criterion can more accurately predict the failure envelope of the composite material under complex stress. And the core idea of longitude compression, compressive failure criteria is established the relationship between the microstress and the macrostress, considering initial misalignment, and then to determine the failure by corresponding failure criteria. Compared with the existing experimental results, the proposed criterion can accurately predict the failure envelope of the composite material in the complex. In terms of the FEM-based failure criteria, we have carried out research on multi-scale analysis based on the idea of stress-strain amplification matrix proposed by Stanford University. Under the periodical arrangement of assumption of the fiber and the matrix stress applied on the laminate can be equivalent transformed to the stress applied on the RVE as shown in figure. Therefore, the microscale stress in fiber and the matrix can be obtained by FEM analysis on the RVEF. The fiber failure is determined by the matrix stress criteria, and the matrix failure is judged by the stress in invariance criterion, which contain two failure modes, namely matrix expansion failure and matrix distortion failure. The critical failure parameters of the fiber can be obtained directly from the unidirectional test strings. And the critical failure parameter of the matrix are obtained by off-X experiments. The tension failure behavior of the open hole laminate was simulated using this method. And the two open hole laminates have a different failure mode, brittle failure mode and pour out, respectively. And the compression failure behavior of composite open hole laminates was also simulated. The results show that the method can accurately predict the progressive failure process of composite open hole laminates and compressive load. The last section is future development trend or some research. The first one is the uncertain failure prediction. The dispersion of composite material is a very important issue that is closely related to the safety and airworthiness of the aircraft. In fact, the large number of tests on the composites are aimed at solving this problem. For determining the design value of a composite material, it is not only a question of determining the strength value, but also its distribution. To this end, we have developed a multi-scale model that take into account the dispersion of each factor. We hope that this research will lead to reducing the number of test specimens used to determine the material allowable value in the future. And the tensile property of the woven composites contain stitch fiber are used as an example here. At the micro scale, the effect of the uncertainty, such as the random arrangement of the fiber and fiber value fraction and constituent property dispersion and void in the fiber bundle are considered. The fiber arrangement was observed by experiment. The random fiber arrangement model are established, and the strength of the fiber bundle can be obtained by considering the failure of fiber matrix and interface under specific load. the distribution of fiber bundle property is obtained through a large number of simulations. And the bottom left two figures gave the property distribution for different fiber value friction. At mesoscale, the effect of fiber bundle property dispersion, matrix property dispersion, and void between the fiber bundle was considered. And based on the woven form, unit cell model is established for the mechanism analysis. The failure strength of the single layer can be obtained by considering the failure of fiber bundle and matrix between the fiber bundle and the specific load. And the strain distribution of the woven composite single layer is obtained through the large number of simulations. And the Weber distribution was chosen to fit the strength distribution. At microscale, the effect of a single layer of property dispersion and interlayer matrix property dispersion and the random arrangement of the stitch fiber are considered. A finite element method considering a stitch fiber is established. The strength of a tension specimen can be obtained by considering single layer of failure and interface failure under specific load. The load displacement curve contains the dispersion is obtained and through a large number of simulations, and as shown in the lower left figure. The strength distribution is shown in the lower figure, right figure. And the prediction as a dispersion of a composite property is achieved by the multi-scale simulation calculation. And another hot part is residual stress in composite processing are also very interesting to us. In our experience, the effect of the process residual stress on structural strength composites is likely to be about 10% and even higher for bad structural design and the process. In this area, the research we first need we first need to calculate the process stress more accurately and combine this with external force to determine the strength of the composite material. And two methods can be used to study the effect of the remote strength on the mechanical property. And the MMF multi-scale analysis measure can be simulated the method based on the micro-scale method. The micro-scale finite element model of unidirectional laminates is used to study generation of the micro-scale residue stress and their effort on failure strength under the transverse law. The results show that due to the residue stress, the stress distribution inside the matrix and transverse failure strengths are changed. The thermal stress are compared with the stress on the interface, leading to an increase in transverse tension strength and a decrease in the transverse compression strength. And the residual stress will lead to the change of the stress distribution in the laminate and the transverse tension stress. The failure mode will also be different. When considering the residual stress, the initial position and the crack was changed. The strain corresponding to the crack initiation and the propagation was also modified, and the crack growth rate became faster. The residual stress will cause change of crack initiation, position and in the laminate, and the transverse compression stress, and the corresponding strain for crack growth will also change. after the initiation of the crack is delayed, and the crack growth rate will slow down. And the last one is the predicting CAI performance of composites based on the CNN, that is the convolutional neutral network. We propose a method for predicting compression residue trains after impact based on the convolutional, just CNN, in order to reduce the training parameter and prevent overfitting. The convolution and the pooling operation was performed. The method took the NDT image as input and the compression and the compressive residue trains labor as output for the training, and the final prediction accuracy reached more than 90%. The core of the predicting is whether the CNN model can extract the key graphical information that affect the compressive residue trains after impact. We output the intermediate layer image, and the results demonstrate that the convolution kernels can automatically extract the damaged feature. And CNN also used to predict the properties of the composite unidirectional laminates. RES with different fiber value factor and different fiber arrangement are generated by the random algorithm. The stress strain curve of RVE with a different fiber arrangement was obtained by the microscale finite element simulation. And then the prediction model of composite properties is established by training CNN model. The trained CNN model can predict the stress strain response of the RVE directly from the fiber arrangement. And here the reference of this report. Thank you.